So today our first speaker will be Ramlal Unnikrishnan from the Chalmers University in Sweden, and he will be talking about evolved stars, and his title is Charting Circumstellar Chemistry of Carbon-Rich AGB Stars. So Ramlal, you can start.
Yeah, can you all hear me?
Yeah.
And you can see the presentation.
Very good.
Yes. Okay, so let's start then. Yeah, my name is Ramlal. I'm a second year PhD student in Chalmers, Gothenburg. So I'm going to present here today some ALMA observations, band 3 of the circumstellar envelopes of 3 carbon-rich AGB stars. Yeah, before I begin, I would like to say that it's good to start with some evolved stars after all the extragalactic and star formation talks that we had mostly yesterday. And also thank you for allowing me to speak here to the organizers. And yeah, so before we go into the data, let's briefly discuss what asymptotic giant branch stars actually are and why it is crucial to study these stars. So as you can see here, these stars are moving, they are expanding and cooling in the HR diagram, moving right and upwards. So these stars are late evolutionary stages of low and intermediate mass stars. And our sun would also become an AGB star at some point in its late evolution. And these stars are characterized by high luminosity, a very convective envelope, and very high mass loss, which leads to a lot of interesting chemistry, as we will see. And so here is a schematic diagram of the structure of an AGB star. So these stars have an inert carbon-oxygen core at the center, and then some shell fusions of helium and hydrogen outside it. And if we see the highlighted part, you'll notice that what we are going to look into today is the circumstellar envelope of these stars, where most of the interesting carbon chemistry happens. And I would like to point out that this diagram is not to scale, because the circumstellar envelope is actually huge compared to the other regions. And as you can see, it ranges from around 10 stellar radii to 10,000 stellar radii. Actually, I made a mistake there in the R, but yeah. Why do we need to study these stars? These envelopes are very rich in molecular chemistry. Particularly, we are going to look at a subcategory of these stars called carbon-rich AGB stars. So what happens in the evolutionary process of these stars is this shell burning of helium and hydrogen, then the helium shell keeps turning off and on depending on how much fuel is actually there. And since the hydrogen layer above it will keep on contributing more and more helium, intermittently the helium layer turns on, and this process is called a helium flash or a thermal pulse. And during these processes, the stellar envelopes and the atmosphere become deeply convective, and this dredges up, or this brings up, the nucleosynthesized carbon and other heavy elements from the core region to the circumstellar envelope. And that is how these envelopes become very rich in complex molecules and polyaromatic hydrocarbons, etc. And then these stars are also major contributors to ISM chemistry, so the chemistry of the galaxy in general, because these stars have a very extensive stellar winds, and these circumstellar envelopes are slowly being ejected into the surrounding ISM. And so these stars are perhaps the biggest contributors to the chemical replenishment of the interstellar medium. So with that being said, let's go for an overview of the project here. So we have, what we have is ALMA band 3 spectral line survey of 3 carbon-rich such AGB stars. And you can see a sample of the survey here. And so we already have single-digit surveys performed much before in 2003 by Woods et al. And why we decided to do an ALMA survey again on top of the single-digit survey is because if we need to calculate exact abundances, we need to know where this emission is coming from spatially. And with the high resolution and sensitivity of ALMA, this is finally possible. And so here is a table showing the 3 sources. And if you look at the values in the table, you would notice that these stars have kind of similar expansion velocities and outflow properties. So all these stars have a relatively simple spherical expanding morphology, and they have similar, more or less similar mass loss rates. But you can see a real diversity in the 12C, 13C ratio here. So this is why we chose this particular set of stars, so that we could explore the regime of different 12C, 13C ratios and see how the chemistry is different in these. And I would say that the primary motivation to do this project is that most of the carbon chemistry that of these kind of envelopes that we know today, and what goes into most of our chemical models of these sources today, is always based on more or less one single carbon star called IRC 10-16. And we thought that just having observations of one star going into a lot of chemical models would not be really an ideal scenario. So we wanted to explore a sufficiently diverse range of carbon stars, so as to see how the chemistry would be different or similar. And we chose these stars with different 12C, 13C ratios because that ratio points towards their new difference in nucleosynthetic histories. And so moving on, the data we have is, I would like to say, it's publicly available in the ALMA archive, but there were a lot of issues with the data in the archive. So since this is an ALMA talk, I thought I would briefly point this out too. So what you see here is a channel from the archival image, and this was developed using the clean algorithm, and you can see a whole lot of this extended artifacts here, which we do not believe is real emission. Because our sources are just spherical, and they are not expected to have any kind of these structures. So since this is cycle 2 data, we had instances when the new pipelines even just refused to run on the data. So in the end, I had to do all the calibration and imaging manually with the support from the Nordic ALMA ARC node. And so we managed to reprocess. This is the same channel that you see here. And so we use T-clean and self-calibration wherever possible, even though that did not really help much. And some intensity mismatches still exist between the overlapping spectral windows, but this has been reduced to less than 20%, which is still significant, but much better if you compare to the archival data. And moving on, we also managed to do some data combination with another ALMA data set of these two of our sources in a very small frequency range, of course, not for our whole data. So if you see here, this is the UV coverage of our survey in this frequency range, 87 to 89. And then we combine this with the 2015 ALMA dataset mentioned here, whose PA is Denise Keller, and the UV coverage becomes like this. So now it's more sensitive to both the extended and compact spatial scales. So we have really managed to increase the spatial resolution and sensitivity in these frequency ranges. And as you can see here, on the top left is the concatenator or the combined image, which has clearly, it looks much better than the other data sets. And we managed to enhance these lines like C2H and then the 13C variants of some other carbon chains and so on. We managed to enhance their images and spectra like this with the data combination. And in addition, we also managed to detect some new lines in the combined data because the data combination also increases the signal to noise. So we managed to find these lines. And then, yeah, so when we are talking about a spectral survey of this scale, we really have a lot of emission lines. So around 200 emission lines have been detected per source from around 35 molecules approximately. And as expected, we have a lot of carbon chains and then some silicon bearing molecules, then the typical molecules like HCN, HC3, etc. and CO, of course, and 13C isotopologues of several of these, mostly in IRAS 15194 because it has a very low 12C 13C ratio as we saw in the table before. And we also have a potential detection of methanol, which we have not confirmed yet, but if we manage to do, which I would say is somewhat surprising, methanol has been detected only in one carbon star envelope before. But the line is very weak, so we do not know yet. And then moving on, we have two main kind of morphologies in the emission. So one is a centrally peaked emission where the molecule peaks near the central star, and then we have a ring-like shell emission. So this is HCN, so this is a centrally peaked emission, as you can see, and then here is CN, which is in a ring-like structure. So this is expected because CN is a dissociation product of HCN, so it should appear much further outwards. And you can see here, these are the azimuthally averaged radial profiles. So from this, it's clear that the CN, if you can see my cursor, peaks very close to where the HCN is like ending. So, and then you can see here a few others that I just put for reference, like there's an HC3N. You can even see a spiral there if you want to. And then there's a 13CS, which is also centrally peaked. And so what I like about this is, to me, this shows the power of ALMA, that you are able to just walk through, like step through the circumstellar envelopes radially and see what molecule exists where, as you can see here. So this is a plot of distance versus, it's a plot of distance and shows the peaks of the emission and the widths of the corresponding emission region. So which would mean like, so for example, in the case of the CN here, the peak would be somewhere at this radii from the center and the width would be this. And we managed to get this by fitting Gaussians to the radial profiles that you saw before and getting the full width at half maximum and the center. And even from here, there is a clear trend that the blue lines, blue dots, which correspond to IRAS 07454, we will notice that all the molecules are systematically more at a smaller radii compared to the other two stars. So we have to do detailed chemical modeling, which we plan to do later. But I think that as a first solution, what I feel, this is because the 07454 has a lower density, which we can approximate by the ratio of the mass loss rate and the expansion velocity, which serves as a proxy to the density. And it has a lower density, so the penetration from the interstellar radiation field UV photons is more. So the dissociations and more photochemistry in general happens more inwards and closer to the star than the other two. And I would like to point out that the centrally peaked molecules, so CS, SIS, and SIU, these widths that I show here are probably underestimated because I just made these plots very quickly yesterday from Gaussian fits that are not very good. So I think if we fit multiple Gaussians, we will be able to improve these. But then for the, yeah, so like I mentioned, so this is kind of analogous to chemically stepping through the envelope and seeing the different molecules. And then we also have some initial abundance estimates, which I have to again say are very, very preliminary. So this is done in LTE, assuming excitation, a fixed excitation temperature, 40 Kelvin for the centrally peaked species and 20 Kelvin for the shell species, which is somewhat reasonable considering that this is what has been used in the literature for IRC plus 10 to 16. But then we will again do detailed non-LTE radiative transfer later. But then let's look at what we can broadly see from the abundance plots. So the C2H and C4H abundances in 15194 are really way higher than the other two stars. So the 15194 is in the blue, and then the other two stars are here. So there's more than an order of magnitude difference in the C2H and C4H. So when we first made this plot, we were a bit suspicious, and then we checked with the single dish abundances, and they also correspond to a similar increase. And then I have the abundances for IRC 10 to 16 also here in red, which also more or less correspond to that. So it seems reasonable. And mostly,
yeah, you have 1 minute.
Yes, I think the main reason for this could be that IRC 15194 has been told to have a spiral structure like we saw earlier, which could cause density enhancements intermittently, which could lead to a higher abundance. And then we see trends in SIO, etc., which is also an order of magnitude greater than 10 to 16. So overall, to conclude, what it says is that the carbon stars are more diverse than just IRC 10 to 16. There is differences. Even from the very preliminary estimates, we see differences and also similarities in the chemistry and in the abundances and in where each molecule occurs in the circumstellar envelope. So so what the key takeaway from this, so I don't have any rigorous conclusions as such right now because this is still very preliminary work. And so the next step is, of course, to do detailed additive transfer, and so which would give us a better idea of the differences and similarities in these stars, and improve the chemical models of AGB circumstellar envelopes, which would also go a long way towards understanding the general interstellar medium chemistry in more detail. And so yeah, then we also have Apex band 5 and 6 surveys already observed, which we would add to the radiative transfer, so as to have more species and increase the coverage of excitation conditions. And I think that is all I have for now. Yes, thank you.
Thank you very much, Ramlal, for this panorama on evolved stars, and thank you for going further than IRC 10 to 16. It's very nice to have a view of what is happening on other stars than 10 to 16. I just have a very quick question. So in terms of number of lines, you showed that you detected something like 200 lines in your band. How does it compare roughly to IRC 10 to 16 for the same frequency range?
I haven't looked into properly into the IRC 10 to 16 data yet, because we don't have it as part of our ALMA sample. So I have to go into the literature and see. I don't have an answer right now.
We can maybe take some pictures, some questions from the chat.
Yes, there are a couple of questions. The first one is the difference in 12C, 13C ratio for the 4 stars also related to the initial mass function, initial mass of the star? So that is the mass during the main sequence phase.
Yeah, I'm not really sure, but I think more than the, sorry, this is not the slide, just a second. Yeah, so I think more than the initial mass, I mean, I actually don't know how it mathematically depends on the IMF, to be honest, but I think a more significant result would be on the nucleosynthesis pathways, as I mentioned here. So a star which could, for example, have some kind of more deep convection and hot bottom burning, a process like this, could have a more higher 13C abundance compared to other stars, because then in the CNO cycle, which happens along with the hot bottom burning process, this would convert the 12C into 14 nitrogen and 13C as byproducts. So I think it's more about the chemistry, but could be. I mean, I don't know if it depends on the IMF.
A good discussion to continue in the Slack, I think.
Yes, sure.
Maybe we can take one last question.
Mm-hmm. Yeah, there's another question. What are the differences, the chemistry of HCN and HNC in these objects that lead to such huge abundance difference for those 2 species?
Yeah, so HCN is, I mean, there is even a morphological difference. HCN is a centrally peaked species, and HNC, it appears further outside in a ring-like structure. So the physical conditions where these 2 molecules exist, including the density and the temperature, these are different. But then, like I said, if we really need to see how these conditions are affecting the chemistry, we need to do the detailed chemical modeling with proper density, temperature, and gradients of other physical properties, which is in the plan for the future. But as of right now, from what I have done till now, I don't have a clear answer of why these are different, but I can say that these peak in very different positions within the envelope. So they are not from the same place, so that we can expect a similar chemistry. Yeah.
Good. Still have work to do. That's very good. Thank you very much again for your talk, Ramlal.
Thank you.
So we'll move on to the next speaker.